What's funny is, like,
The correction. On Monday, I said this was a multiplication. It's a plus. I talked about the adjusted displacement ductility, taking into account a bilinear moment curvature curve, which is not necessarily perfectly plastic. I'd originally written this as a multiplication between mu over mu. Is in fact an addition sign.
That's m dot, right?
Yes, your displacement ductility. What I want to spend some time talking about today is modeling. So I've been wanting to spend more time in SAP than I've managed to get to, but I think it's really important to spend time on the concepts, because if you don't understand the concepts, you have no business doing computer modeling. Because computer modeling, as I'll show you as we're walking through this analysis of the homework, can have lots of mistakes that show up if you're not careful. So, one of the big things you want to keep in mind when you're doing this sort of computer modeling is this is an analysis set of software. This is not a CAD piece of software. So you don't want to think in those terms where you're drawing everything in CAD and then it magically knows how to take your CAD drawings and do all sorts of appropriate analysis on them. Finite element software is much, much different than that. It basically solves all your problems by looking at displacements. So you have what are called nodes, these individual points in space, and you connect these nodes with members. And these members have certain properties. So these members can have degrees of freedom, like they're allowed to translate in certain directions, maybe restricted in others, allowed to rotate in certain directions, but not in others. They could be fully free, they can rotate in every direction, they can translate in every direction, but you're formulating your analysis essentially based off the properties of this member and how it connects to nodes. So this method has no knowledge of, let's say, CAD drawings, where you're developing, let's say, the full geometry of a section, and then implicitly just knows everything about that. If you want to use finite element modeling to kind of capture that sort of behavior where you're looking, let's say, a wide flange beam, you want to model that in great detail, you can do that by using nodes, but you don't want to think of that process as being kind of synonymous with the analysis we want to do here. We're looking, let's say, a system level performance of this whole frame. So keep that in mind. So I'm just going to start kind of from the basics in SAP. I know I've kind of jumped around a little bit with it so far, but I want to go kind of from the ground up. We're going to build the model. I basically want to solve your homework problem in SAP, but we'll also verify different steps as we go along. You can check to see you're correct if you're moving from push to push. So SAP has a lot of defaults you can use. I'm just going to do a 2D frame, starting in units of kips, feet, and Fahrenheit. And so here you can define different things. I'm just going to have a one story, one bay frame. My story height will be 30 feet, and my bay width will be 60 feet. And I'm not going to worry about defining the sections right now, because I'll do that in a minute. So if I do this, I end up with a window that looks like this. I generally don't like the isometric views being right next to it. If I want to look at an isometric view, I'll do that on my own. So usually get rid of that. I also tend to get rid of the grid. So view, show grid, get rid of those. You can get rid of the axes too if you like, but I also like to show joints for small frames like this. So I go to my settings button up here, to your display settings, this little check mark box, and then I'm unchecking invisible joints. And so this makes my joints show up 1, 2, 3, 4. So generally one of the first things you want to do is you want to set the boundary conditions of your problem. You do this by defining joint restraints. So when I said finite element packages solve things by displacements, you basically define in your model what individual joints can do in terms of their displacement behavior. So for our structure, we're interested in, let's say, just this two-dimensional analysis. So I'm interested in, let's say, rotations along, let's say, the y-axis, displacements potentially in z, and displacements potentially in x. So I can do all this manually, but another good way to make sure you're having any mistakes, you can set analysis options. And SAP gives you a lot of defaults here. It means just basically are modifying your rotations. So you can see your available degrees of freedom are up here. UX would be global displacement in the X direction. UI would be global displacement in the Y, global displacement in the Z, and then rotation along the X-axis, rotation along the Y-axis, rotation along the Z-axis. So for our frame, we're interested in a plane frame. So I can either manually check off displacement in Y, rotation in X and Z, or I can just click plane frame and it'll do that for me. So that's all these are doing. So now I want to model our homework problem. We had a fixed frame. So right now, this little icon here is denoting a pin. And we can verify that by doing assign joint restraints. And SAP will now tell you what are the restrictions on this joint. You can see this is restricted to translation in all directions. So this would constitute a pin, which means it has free rotation in all directions as well. If I want to fix this, I can either fix all the rotations by hand, or SAP also tends to give you these nice predefined as well. You have a roller detail. This only fixes translation into 3, so this would allow translation along the X, but restrict translation in the Y, or the Z in this case. You have a pin, which is going to fix all these translations, not just your Z. Or you have a fixed, which also fixes these. So these, or you have a free in this case. So these buttons here are just quick ways of defining your degrees of freedom that this joint is allowed to have. So I'm interested in having fixed bases of my column. This icon here denotes a fixed base. So I'll go ahead and fix the other one as well. Joint restraints. Okay, so the next step, essentially, we want to A, define the loads on this frame, and B, set up the geometries. So there's something to keep in mind when you're defining, let's say, the properties of this member. And that is, SAP doesn't really care, per se, what all the geometric kind of details are of this member. It's mainly going to care about what are the geometric properties, i.e., what's the moment of inertia of this section? What's the cross-sectional area? What are all these properties you'd solve, let's say, by hand for a section? Whether or not you give it that section directly, it doesn't particularly care about. So you don't have to have, let's say, a wide flange beam to represent a wide flange beam. You can come up with something that's synonymous for that, or you can find properties on your own. So for example, we knew the dimensions of the beams, or the columns in this case. That came from homeworks 4 and 5. But I didn't give you any specific details about the beam, other than it's got 2 times the moment of inertia of this guy down here. So there's ways we can account for that. And so because I was using a transform moment of inertia, and this would also take into account, let's say if you're using the cracked concrete properties, if you're doing a reinforced concrete design, that's really what you want to do. You use the cracked moment of inertia. So you look at, let's say, ACI for that information for getting your cracked concrete moment of inertia. But I'm using a transform section that takes into account steel and concrete for I. And so I don't necessarily want to just put in this rectangular section with just concrete and have it calculate the moment of inertia for me based on a rectangular or a square section. I want to give it the section manually. So what I'm going to do is I'm going to kind of trick SAP. And so I'm interested in let's say I want a moment of inertia of 24 feet to the 4th. That's what was given. So I can actually come up with an equivalent circular section for this based off the fact that I know the moment of inertia for a circle is going to be pi over 64 times diameter to the 4th. So I can actually back solve in this case. So if I'm interested in a diameter equivalent in feet, I can just take this moment of inertia of 24 feet to the 4th, multiply it by 64, divide it by pi, and take this whole thing to the 1/4 power. This gives me an equivalent diameter of 4.07 feet. So I'll actually feed this into SAP now as a geometric property. So to do this, I go to define section properties. Go over to frame sections. Gives you a generic section to start out. You can go add new property. In this case, you can pick whatever material you want. This just defaults to different section geometries. I'm just going to look at a concrete section because that has circular here. I'll define the material in a minute. So I'll just select circular. And you can see now it asks me for a diameter of this section. This is where I put in my diameter of 4.702. Well, you should see now, as you go to section properties, I have a moment of inertia around the 3 and the 2 axes of 24. When you're doing a plane analysis like this, you're interested in the moment of inertia around the 3 axis. So the 3 would be rotation about y. 2 would be rotation about x. So for my rotation about y, that's the one that's of interest to me, is 24 feet to the 4th. So the way I'm going to set up my beam now, you'll notice if you go here to set modifiers, it lets you scale different values of interest for this cross section. So because all I know about the beam in this case is that it has twice the moment of inertia, I can just go into this moment of inertia multiplier here, and I can multiply it in this field. But in this case, I'm just doing the column for right now, so I'll leave this as 1. I'll come back to this in a minute. And so we can call this, let's say, column. Now I'll add a copy of the property. So this is basically the same thing. I'll call this beam. But now I'm just going to come down to the set modifier, and I'll increase my moment of inertia by a factor of 2. Because that was the only difference. We had I versus 2I. So this is why sometimes normalizing can be really helpful. It lets you, let's say, generate lots of different cross sections, but instead of having to give each one its own individual properties, if they're relatively generic, you can just come in here and use set modifiers to quickly change different parameters and have, let's say, just kind of a default section, and then you modify that section for other applications. So I've got my beam and my column now. I now want to assign them. I can assign frame, sections. I've selected my 2 columns here, so I'm going to select column. It now tells me right here that this is column, section. I'm going to do the same for beam, assign, frame, sections, beam. I'm now interested in coming up with the loads on this frame. So SAP has several ways of doing that. You can either apply point loads to joints, or you can apply point or distributed loads to members. So in this case, we had a distributed load that was applied to this beam of 20 kips per foot. So now I want to assign not frame, but frame loads. Distributed. My direction here is gravity. This would be your negative z. And you have the option of having, let's say, triangular loads or different load distributions. You use that, let's say, if you have snow or some other, let's say, nonlinear load pattern. You can account for that here. I'm just going to use uniform load and 20 kips per foot. Always check your units. I have kips and feet. So now if I want to do, let's say, just a basic dead load analysis of this, I can look at load patterns. Now to apply that under dead load type, what you'll see here is a self-weight multiplier. This allows SAP to basically look at the geometry of your cross-section. You can give it a weight relative to the volume, and it can automatically calculate dead loads for you. This is really handy in some cases. In our case, we don't need this feature because we've already prescribed a load of 20 kips per foot. That's taking into account dead load and wherever loads are up there. So I want to change this self-weight multiplier to be 0, and then modify load pattern. This is just my dead load. And now let's just go ahead and see what the dead load analysis of this frame looks like. So I can run analysis, my dead load case. And let's see if we get something that looks like what we should have got from our hand calc. So for reference, our hand calc for this homework should give us a frame look something like this. So you would have found that this frame has no sway, because if you look at these forces at the base of the frame, they're equal and opposite. You have no residual lateral force, so you didn't have to do any sway correction analysis for this frame. If you had some asymmetry in the frame, i.e. this was a pin detail, like our example, then you would have sway. When you have a perfectly symmetrical frame, you're going to have these balances out. So because we had no sway to worry about, we don't have to account for that in here. It's a few extra steps to account for sway and sort of analysis. So I'm just leaving that out for our discussion. So if I'm interested in looking at the end moments for this beam, or for this frame, you have your results buttons displayed up top here. So you have basically your undeformed shape. You have the deformed shape, so we can look at the deformation of this due to dead load, for example. Doesn't see too much, increase the scale factor. So you can see this is what the deformed shape of our frame looks like from dead load. Now I'm interested in comparing, let's say, the moments and the base shears of this frame with our hand calculation and see if we have something that matches. So moment 3.3 is of interest to us. Oops. I always like to show values on the diagram. And I also like to do the American side of things and have the moment diagrams upright like this. So positive bending moment, like so. So let's see. This analysis says the moment here is 3934, and the moment at the base is 1870. So we have a problem. Our hand calc is not agreeing with our computer calculation. Which one do you guys think is correct? Why did you say that?
I'm guessing it has to do with the joint assignment on the top.
No, all our assignments are okay. The load's applied correctly. Think about how we're formulating our hand calculation. What process were we using to come up with those moments?
Moment distribution.
Moment distribution. And what were we looking at specifically with moment distribution? What did you look at when you look at, let's say, the distribution factors between different members?
Stiffness.
What type of stiffness?
Translation.
It's rotation.
Rotational stiffness for moment distribution. So you're looking at the rotational stiffness. So you're looking primarily at flexure. Okay. So this calculation is correct for purely flexure. But what SAP is going to be doing by default here, it's going to include things outside of flexure as well, right? If we look at not just the moment diagram, let's look at, let's say, the shear diagram. And what do we notice for this frame? We have shears in all the members. So what other types of deformation do we expect to see in here? We expect to see shear deformation show up in these formulations. So you can account for that in moment distribution as well. It's capable of being done by hand. It's just a lot more tedious, and we generally avoid that. But what else do you have in this frame? You also have axial forces as well. So not only do you have flexural deformations occurring here that contribute to those end moments, but you also have shear deformations and axial deformations. So it's not so much that one is right and one is wrong. They're just considering different things. So let's go through and let's tell SAP, I don't want you to consider shear deformations and axial deformations. I only want you to look at flexure because our hand analysis is a flexure-only comparison at this point. So generally speaking, if you're trying to, let's say, tune a model and you're starting out simple and make sure your computer model is doing what you want it to do, you, let's say, have flexure analysis as kind of one of your go-to hand calculations. So you could check your flexural analysis by hand with your computer program. You can make sure that key components are working beforehand. And then you can go in and add more complexity. Then you can start worrying about shear deformations and axial deformations. But one of the big things to know about this type of analysis is the more complexity you get, the faster you get, the harder it is to troubleshoot and get a good reliable model. So generally speaking, you want to start very small and work your way up. That's why these types of analyses can be very helpful. You have, let's say, a relatively simple model. You can do a hand calculation, get a good approximation, and you can compare between the two. And if you can verify that your hand calc and your computer calc are matching, then you have something to go off of. Then you can add more features in. You can start looking at different degrees of freedom, changing different things, doing different parameter studies, if you will. But let's go back now, and let's take into account that there's shear and axial deformations present in these members. So if I go back to my section properties, go to frame sections, go to, let's say, column, modify the property. I can go to set modifiers again, and you'll see we have shear area as a modifier here, and we also have cross-sectional area. So what I essentially want to do is say axial deformations are negligible. What does that mean? It means you have a member which is essentially axially rigid, which means it's incredibly stiff. How does stiffness contribute axially to members? Well, your axial stiffness is AE over L. So how would you increase the stiffness of these members? You can increase either A or E, but E in this case is being used as an actual value for, let's say, our deformations of this frame. So we don't want to mess with E. L is also kind of a fixed value of our frame. That's an actual geometry. But A, we're not really using for anything. It's kind of a throwaway value in this case because that's only really used for axial deformations. So to get away from the axial deformation problem here, I can just, let's say, make this member really stiff. How stiff? I'm just going to use a factor of 1,000 here. But you've got to be a little bit careful with this, because remember I said at the very beginning of this class, this is a stiffness method solution. So the way finite elements are solved is using stiffness method. And that takes into account, probably should erase that, but that's okay. For a multi-degree of freedom system, your forces that develop in your frame are equal to a stiffness matrix, which is relating the stiffness of each member and each node together, and displacements. And I said that this is a displacement-based method, so it's solving for displacements. Generally, you're interested in, let's say, forces and moments and such, though. So how does it get those? It inverts the stiffness matrix. So you have to be very, very mindful of this. What happens when you invert matrices? Potentially lots of things. Right? That's why you have, let's say, a background in calculus coming into this sort of stuff, because you have to be wary about this. If you have, let's say, really big disparities in values, i.e. you make one of these stiffnesses way too big, what can happen is you won't ever get convergence of this matrix. It tries to invert this matrix, one of the numbers is way too high, and it can't ever reach a solution. And so you may not even be able to run your analysis if you make this too high. The caveat in some cases is, this may be too soft for you. It may be inducing effects into your model that you don't want there. So oftentimes you'll hear, let's say, nonlinear analysis called an art. And the reason for that is you have to find a good balance of how do you change, let's say, stiffnesses of members that you're trying to fix in certain ways to give you a correct result without making them, let's say, too soft or too stiff. Because too soft or too stiff, if they're too soft, they're actually influencing numbers a lot. If they're too stiff, you can't actually get a solution. There's a fine balance to be had there. In this case, I'm just going to use a factor of 1,000 on the cross-sectional area. I know that works pretty well, just from playing around with it a little bit. This takes into account the axial deformations in the frame. I also want to set the shear area in this case equal to 0 as well. So normally shear deformations, you're usually okay to ignore them for the most part. You have deep sections, let's say, you get a lot more influence of shear deformations. So if you recall from elastic theory, you have a beam, and you're looking at the shear stress distribution, say your height versus tau. You have this parabolic distribution of shear, right? Tau is VQ over IB. Then for a moment, let's say you have a linear variation. MC over I. What will happen is if you get a member that's sufficiently deep, the shear stresses will start to grow significantly faster than the bending stresses. So this means shear deformations can become a significant factor if your member's too deep. So lots of little things you want to keep in mind when you're trying to play around with these values and changing things in your computer model that if you try to, let's say shear deformations are negligible, you have to make sure that they actually are. If you have a really deep beam, they may not be. But for our problem, we're going to go ahead and ignore those. So I've made my axial Stiffness now really high. I said the shear area for this is 0. So with the shear area of 0, I get no shear deformations. I also want to change the beam. I'll also give this guy 1,000 on the multiplier for area and 0 for the shear areas. All right, so now let's see. Go ahead and run this analysis again. Look at moment 3.3. We now see, and I erased it, I'm sorry, but we now have 4,000 kip feet at the joints, which is what we had from our hand analysis. And we also have 2,000 kip feet at the base. Yes, it's not exact, but you'd increase your axial stiffness a little bit more if you want that to be more exact. So we can play around with that just so you can see the differences. We define our frame sections. Let's say we only use an axial or an area modifier on members of 10 instead of 100. You can see we're still not quite converged. That's actually pretty close. Instead of 3930 here, we have 3998. So still pretty close, but it's not quite 4,000 either. So you can play around with these. So even with a multiplier of 10, you get a pretty good result in this case. Let's go ahead and bump those back up to 4,000. Or 1,000, sorry. Okay. So that's good for our dead load analysis now. You have some way to compare your hand load or your hand calc of your dead load moments and shears with your computer analysis. What are we also interested in doing? We're interested in pushing this frame over and seeing how plastic hinges and such develop. So before I start developing the hinges stuff, I'll just show you how to walk through this kind of sequentially and check your work along the way. So I want to define a new load pattern. I'm going to call this guy push. Call it other. Add a new load pattern. And so I essentially want to put on now this unit load of 100 kips. Right? We said everything was based off these unit loads of 100 kips. So I'm going to see what are the end moments that developed just from a lateral push of 100 kips. Because that was one of the big things we did with our hand calculations. So we should also be able to check that in SAP. So I'm just going to come to the top of the frame here, top left. I'm going to assign joint loads, forces. I didn't worry about the load pattern before because we only had the dead, but now we have multiple loads, so I'm going to select push. My units are in kips and feet. My global force in the x direction is what's of interest here. Let's say I'm just going to apply 100 kips. So we can, once again, draw this frame out, just so we know what to expect coming in. See if we get things that match up. Of course, all the units here are in kips and feet. This will be associated with a push laterally of 100 kips. Run my analysis. Now I'm going to be interested in looking at push. Oops. Run down. So it's defaulting to the dead load case, but if you come back up here to your analysis buttons, you can look at frames, cables, etc. So instead of looking at dead, we'll look at push. And once again, interested in moments, 3, 3. So there we go. It says the moments at the joints are 642. We have 643. And the moments at the base are 857. We have 857. So we know we're in good shape here. This shows us that our unit load of 100 kips is reflective of what actually happens. What happens next? Now we start having hinges form. So if you go through the push analysis, you would have found that our first hinge forms at joint C, which would be this guy up here. I'll go ahead and unlock this. So up here at the top of the column on the right is where our first hinge forms. So the way we can model this hinge forming is we can release the moment at that joint. And this says the moment here has no more, or the joint has no more moment capacity. So if I go to this member, I can assign frame releases and partial fixity. This is also how you set up, let's say, trusses, which have a bunch of interconnected members with no moment capacity between members. Everything's a pin. Right? So you go to releases partial fixity. You have your moment 3, 3, which is of interest here. I'm just going to select the end because by default SAP will start members start to end, with the start being at the base. So if I do this now, you'll see it shows us a little icon here. This means there's no more moment transfer through this joint. So now I can do this push again. And also one thing before we do that, we should define materials. I didn't set the E for this. E for this material is 4110 KSI. So I'm just going to modify the standard concrete. So 4,000 PSI is what SAP calls a normal concrete. You can come in here. I'm going to change my units to kips and inches temporarily. And for modulus elasticity, SAP defaults to 3605, which is what you get from the design equations for 4 KSI structural concrete. But we're going to use 4110 because that's what came from our material models for this particular section. Everything else we're not particularly worried about at this point. So we're just going to change to 4110. We can also compare, let's say, displacement and stuff in this case as well. Now we can run the analysis again, and let's see what we get. So our hand calc